The field of astronomy has been revolutionized by telescopes that allow humans to peer into the depths of space, revealing celestial wonders previously unimaginable. At the heart of this optical revolution are two primary telescope designs: refracting and reflecting telescopes. These instruments, while serving the same fundamental purpose of gathering and focusing light from distant objects, employ distinctly different mechanisms and possess unique sets of advantages and disadvantages. Refracting telescopes utilize lenses to collect and bend light, providing sharp, high-contrast images ideal for planetary observation, while reflecting telescopes employ mirrors to gather and focus light, offering greater light-gathering capacity at lower costs, making them superior for observing faint deep space objects. Understanding these differences is crucial for both amateur astronomers selecting their first telescope and professionals designing advanced observatories, as the choice between these two designs significantly impacts observational capabilities, maintenance requirements, and overall performance. The primary difference between reflecting and refracting telescopes lies in the fundamental method they employ to collect and focus light to form an image. Refracting telescopes, commonly known as refractors, utilize a lens as the primary optical component. This lens, typically convex in shape, collects incoming light and bends it, refracts, through the lens material, causing the light rays to converge at a focal point where the image is formed. The optical path in a refractor is straightforward, with light traveling directly through the objective lens to the eyepiece or camera. This direct optical chain minimizes certain types of aberrations and contributes to the telescope's performance characteristics. Reflecting telescopes, on the other hand, employ mirrors instead of lenses to gather and focus light. The primary component in a reflector is a concave parabolic mirror that collects incoming light and reflects it to a focal point. Unlike refractors, the light path in a reflector involves reflection rather than transmission through glass, fundamentally altering how the telescope interacts with different wavelengths of light. This distinction forms the basis for many of the comparative advantages and disadvantages between these two telescope designs. The reflecting design typically incorporates a secondary mirror that directs the focused light to an eyepiece or camera positioned at a more accessible location, creating a more complex optical path but enabling more compact and versatile telescope designs. The image formation process differs significantly between these designs, with refractors relying on the lens's refractive power and reflectors utilizing the mirror's curvature to focus light. These fundamental differences in light manipulation give rise to distinct optical characteristics, cost considerations, and performance parameters that astronomers must weigh when selecting an instrument for specific observational purposes. Understanding these principles provides the foundation for appreciating the nuanced advantages and limitations of each telescope type in various astronomical applications. Refracting telescopes represent the classical telescope design, first conceptualized by opticians in the early 17th century. The optical arrangement consists of an objective lens at the front of a long, enclosed tube with an eyepiece at the opposite end. This design creates a sealed optical system where light travels in a direct path from the objective to the eyepiece. The objective lens is carefully crafted from high-quality glass with a thoughtfully designed form to minimize distortion and aberration, while the eyepiece lens typically functions as a simple magnifying lens that can be changed to adjust magnification levels. The long, thin tube serves not only to maintain precise alignment of the optical elements, but also acts as a light blocker, preventing stray light from entering the optical system and degrading image quality. The sealed nature of refracting telescopes contributes significantly to their operational characteristics. With the optical elements permanently enclosed within a tube, the internal environment remains protected from dust, moisture, and air currents that could otherwise degrade image quality. This design feature minimizes the need for frequent cleaning and realignment of optical components, contributing to the refractor's reputation for reliability and low maintenance requirements. Additionally, the closed tube design prevents thermal air currents from affecting the optical path, resulting in more stable images, particularly during extended viewing sessions, when temperature changes might otherwise impact performance. Refracting telescopes offer several distinct advantages that make them particularly well suited for certain astronomical applications. Among their most notable benefits is superior resolving power per inch of aperture, allowing them to reveal fine details on bright objects like planets, the moon, and double stars. This exceptional detail resolution is complemented by outstanding image stability, particularly in less than ideal viewing conditions where atmospheric turbulence might compromise observations with other telescope designs. The stable performance of refractors stems partly from their unobstructed optical path, with no secondary mirrors or supporting structures intercepting incoming light. The unobstructed light path in refracting telescopes contributes to their excellent contrast characteristics, making them ideal for observing subtle features on planetary surfaces or discerning faint companions to bright stars. Without a secondary mirror or spider veins to cause diffraction effects, refractors produce clean star images without the diffraction spikes commonly seen in reflector images. This absence of diffraction artifacts is particularly valuable for certain types of astronomical photography and detailed visual observation. Furthermore, the near-permanent optical alignment of refracting telescopes represents a significant practical advantage, requiring minimal maintenance compared to reflecting designs that need periodic collimation, realignment of their mirrors. Another notable benefit of refracting telescopes is their immunity to thermal impairment thanks to their closed tube design. Unlike reflecting telescopes with open tubes that allow air currents to disrupt the optical path, refractors maintain consistent performance as ambient temperatures change throughout an observing session. This thermal stability contributes to sharper, more consistent images, especially during long observing or imaging sessions. Additionally, the images produced by high-quality refracting telescopes may be sharper and less prone to aberrations and distortions than those from comparable reflecting telescopes, particularly for bright objects within our solar system. Despite their many advantages, refracting telescopes suffer from several significant limitations that restrict their utility in certain applications. One of the most substantial drawbacks is their prohibitively high cost for larger apertures compared to reflecting telescopes of similar size. The requirement for large pieces of high-quality optical glass that must be precisely ground and polished on both surfaces makes large aperture refractors extremely expensive to manufacture. This cost factor effectively limits the practical size of refracting telescopes, with truly large instruments being rare outside of historical observatories built in the 19th and early 20th centuries. Perhaps the most significant optical limitation of refracting telescopes is chromatic aberration, the inability to focus all wavelengths of light at exactly the same point. This optical phenomenon occurs because different wavelengths of light bend at slightly different angles when passing through glass, causing color fringing around bright objects and reducing overall image sharpness. While modern achromatic and apochromatic designs mitigate this issue, they do so at considerable additional expense and can never completely eliminate the problem as reflectors do. This inherent limitation makes refracting telescopes less ideal for certain types of astrophotography and spectroscopic work, where precise color rendition is critical. Another practical disadvantage of refracting telescopes stems from their typically long focal ratios, which result in physically long optical tubes that can be cumbersome to mount, transport, and store. A high-quality 6-inch refractor might have a tube length exceeding 6 feet, requiring substantial mounting hardware and making it challenging to use in limited spaces. This extended length also contributes to the overall weight of the instrument, often necessitating heavier and more expensive mounting systems. Additionally, the physical limitations of lens manufacturing technology make truly large aperture refractors, over 8 inches, exceedingly rare and extraordinarily expensive, restricting their light-gathering capacity compared to much larger reflectors that can be produced at reasonable cost. Reflecting telescopes revolutionized astronomy when introduced in the 17th century, offering an alternative optical design that overcomes many limitations of refractors. The fundamental component of a reflector is its primary mirror, typically concave and parabolic in shape, which collects incoming light and reflects it to a focal point. Unlike refractors with their direct optical path, reflectors typically incorporate a secondary mirror that intercepts the converging light beam and redirects it to an eyepiece or camera positioned at a more accessible location. This arrangement creates a folded optical path that allows for more compact telescope designs while accommodating larger light-gathering surfaces. The construction of reflecting telescopes offers significant manufacturing advantages over refractors. Since mirrors only need one precisely shaped and polished surface, unlike lenses that require two, they are easier and less expensive to produce, particularly in larger sizes. The primary mirror in a reflector is typically made from glass or ceramic materials with a thin reflective coating of aluminum or silver applied to the front surface. This reflective surface interacts with light in a fundamentally different way than the refractive elements in a refractor, as reflection does not depend on the wavelength of light, eliminating the problem of chromatic aberration that plagues refracting designs. Several variations of the reflecting telescope design exist, including the popular Newtonian configuration with its secondary mirror positioned at a 45-degree angle to direct light to an eyepiece on the side of the tube, and the Cassegrain design that uses a perforated primary mirror with the secondary reflecting light back through this central hole to an eyepiece at the rear of the instrument. These different configurations offer various advantages in terms of compactness, ease of use, and optical performance, expanding the versatility of reflecting telescope designs for different applications and user requirements. Reflecting telescopes offer several compelling advantages that have made them the predominant design in modern astronomy. Perhaps their most significant benefit is the ability to achieve much larger apertures than refracting telescopes at reasonable cost. The primary mirror in a reflector can be manufactured in sizes that would be prohibitively expensive or physically impossible with lenses, allowing for dramatically increased light gathering ability. This aperture advantage translates directly to the ability to observe fainter objects and resolve finer details, making large reflectors indispensable for deep sky observation of distant galaxies, nebulae, and other faint celestial targets. A fundamental optical advantage of reflecting telescopes is their complete freedom from chromatic aberration. Since reflection does not separate light into its component colors as refraction does, reflecting telescopes produce images without the color fringing that affects even the best refractors. This characteristic makes reflectors particularly valuable for astrophotography, spectroscopy, and other applications where accurate color rendition is important. Additionally, mirrors reflect all wavelengths of light equally, whereas lenses may block certain wavelengths, giving reflectors an advantage for specialized astronomical research investigating ultraviolet or infrared radiation. The cost-effectiveness of reflecting telescopes represents another major advantage, with reflectors offering significantly more aperture per dollar than comparable refractors. This economic efficiency stems from the simpler manufacturing process for mirrors compared to high-quality lenses, particularly in larger sizes. The practical implications of this cost difference are substantial, allowing amateur astronomers to access much larger apertures and professionals to build truly enormous instruments like the 10-meter Keck telescopes. Furthermore, Reflecting telescopes are typically less sensitive to temperature changes than refractors, with modern mirror materials having very low coefficients of thermal expansion that minimize focus shifts as ambient temperatures change during observation sessions. Despite their many advantages, reflecting telescopes come with several limitations that must be considered. One significant drawback is their requirement for more frequent maintenance compared to refracting telescopes. The open tube design common to many reflectors allows dust to accumulate on the mirror surfaces, necessitating periodic cleaning. More importantly, the alignment collimation of the primary and secondary mirrors is critical to optimal performance and can be disrupted by transportation or even normal use, requiring occasional adjustment to maintain image quality. This maintenance requirement can be intimidating for beginners and represents an ongoing consideration for all reflector owners. Another limitation of reflecting telescopes relates to their image quality. While free from chromatic aberration, reflectors can suffer from other optical imperfections, including spherical aberration, coma, and astigmatism, depending on their specific design and quality of construction. Additionally, the secondary mirror and its supporting structure, spider, create a central obstruction in the light path that reduces contrast and creates diffraction spikes around bright stars that are absent in refractor images. This obstruction effect becomes more pronounced in designs with larger secondary mirrors, such as Schmidt-Cassegrain telescopes, potentially impacting image quality for certain high-contrast observations. Thermal considerations present another challenge for reflecting telescopes. The open tube design typical of many reflectors, particularly Newtonian models, allows air currents to flow across the primary mirror, potentially causing image distortion as the mirror adjusts to ambient temperature or as warm air rises through the optical path. These thermal effects can be particularly problematic at the beginning of an observing session when the telescope is cooling down to ambient temperature. Additionally, while large reflecting telescopes offer tremendous light-gathering power, their size and weight can make them less portable and more difficult to set up than smaller instruments, potentially limiting their practical utility for casual observers or those with transportation constraints. When comparing refracting and reflecting telescopes, the choice often depends on specific observational goals and practical constraints. For planetary observation, lunar studies, and double star work where high contrast and sharp definition are paramount, high-quality refractors often excel despite their higher cost per inch of aperture. Their unobstructed aperture produces images with superior contrast, and their freedom from collimation requirements makes them more user-friendly for beginners or those who prefer minimal maintenance. Conversely, for deep sky observation of faint galaxies, nebulae, and star clusters where light gathering power is the primary consideration, reflecting telescopes offer decisive advantages through their ability to provide much larger apertures at reasonable cost. Practical considerations such as portability, storage requirements, and maintenance capabilities should also influence telescope selection. Refractors tend to be more compact and robust in smaller apertures up to about 4 inches, making them excellent travel instruments or grab-and-go options for quick observing sessions. Larger refractors, however, quickly become unwieldy due to their long tubes. Reflecting telescopes, particularly in Dobsonian configurations, offer remarkable aperture-to-price ratios and can be more compact for a given aperture, though they typically require more careful handling to maintain optical alignment. For astrophotography, both designs have their place, with premium apochromatic refractors excelling at wide-field imaging and large reflectors providing the aperture necessary for detailed captures of distant objects. The choice between refracting and reflecting telescopes ultimately represents a series of trade-offs between optical performance, cost, convenience, and intended use. Neither design is inherently superior to the other. Rather, each excels in specific applications and observing scenarios. Refracting telescopes offer exceptional image stability, contrast, and convenience, but at higher cost and with inherent chromatic limitations. Reflecting telescopes provide superior light-gathering capability per dollar and freedom from chromatic aberration, but require more maintenance and may produce images with less contrast due to central obstruction. Understanding these fundamental differences allows astronomers at all levels to select the instrument best suited to their observational goals, budget constraints, and maintenance preferences. Many experienced observers eventually acquire both types of telescopes, recognizing that these complementary designs each offer unique windows through which to explore and appreciate the wonders of the night sky.